Finding Wronskian of nth order differential equation without solution. So my goal of the video is to be able to find the Wronskian of this nth order differential equation over here without like explicitly calculating the solution. But yeah, first of all, let us begin with what is Wronskian and what does that mean? Like how do we actually find it normally, right? So let's go with those stuff and then we will gradually proceed to this thing. So basically, let's say we have this homogeneous second order differential equation. Let's say this is p1 of x y prime plus p2 of x y is equals to 0. We know that since it's a second order differential equation, it will have two solutions, right? Let the first solution be y1, second solution be y2, right? And now, where the Wronskian comes in use is, so basically, now if you have to find general solution, we first have to determine if these two form a fundamental set of solution or not. And for the fundamental set of solution, like we first find the Wronskian, and we check if the Wronskian is 0 or not, right? And if the Wronskian is not 0, so then we can form, then we know that they form a fundamental set, and we can write general solution like this. So okay, and normally like Wronskian is calculated as the determinant of y1, y2 and y1 prime. That means derivative of y1 and y2 prime, right? And this determinant is Wronskian. But we see that to find the Wronskian, we need the solutions in hand, and then only we can do it, right? So yeah, so basically there's an alternative to this. There's also a way we can find Wronskian even without the solutions. So yeah, that's what we're going to discuss in this video. And the way is actually this, it's already given over here. The Wronskian, let's say for this differential equation will just be some constant times e to the power negative integral from t naught to t, and then this p1 of x dx. This doesn't give us like really the complete Wronskian, but Wronskian accurate up to certain constant, right? So, and that does its job because it gives Wronskian up to a constant, and uh, that's actually helpful if because we can assume the constant to be non-zero, and then yeah, and then do the things. Okay, now let's see how we actually get this formula. First of all, we will see it for just a second order differential equation, and then we can then also do for nth order. Okay, so we see that Wronskian is actually this determinant, right? Yeah, y1 y2 prime minus y1 prime y2. Okay, now what I will try to do is I will try to find the derivative of this determinant, right? And to find derivative, I can actually use this expanded form as well, but there's an easier version if I just try to do it directly. There's a thing called there's a thing called I forgot the name whose formula was that, but yeah, there's a formula. What that formula says is, let's say there are some functions. Let's say if you want to find, let's say a b c d e x g h y f g h y. Now let's say if I g h I, if you want to find derivative of this function, right, with respect to x. Now what that formula says is, you can first take derivative of the first row, right, and rest of the rows as it is. Yeah, and then again you add. Now you just take the derivative of the second row. I think this is a Leibniz formula. I got it now. Leibniz formula. There's also another formula to find derivative of determinant, which is Jacobi's formula. But yeah, like that one will not really be helpful here, but this one will be helpful. And also the third way it will be just to expand and find determinant. But among these three, this is the most helpful way. So we are going with that. So I'm just trying to introduce how like what's the Leibniz formula way to find determinant, to find derivative of determinant. Okay, I of x, and again plus a of x, b of x, c of x, d of x, e of x, f of x, then g prime of x, s prime of x, I prime of x. Okay, so the determinant of this determinant is actually the sum of these three determinants, right? And the thing that has happened is we basically take derivative of one row at a time and then add them up. So yeah, so this is the thing that we're going to use. Now, using this thing, let us try to find derivative of our Wronskian. And yeah, and the thing is, the reason we are taking derivative is like there will be some cancellations, and we will be able to find a relationship between the derivative of Wronskian and actual Wronskian, and that will help us to get this equation, right? Okay, let's see. So we have Wronskian as determinant of y1, y2, y1 prime, y2 prime, right? Now if I take the derivative, this will be y1 prime, y2 prime, and second row as it is. Now first row as it is and derivative of second row, double prime, double prime. So you might have noticed that since both the rows, like we know that if any two rows are identical up to a constant multiple, the derivative of that matrix is 0, right? So here, like both of these rows are like identical up to the constant multiple of 1. So that's 0. So you see that there's some really good simplification. This just becomes 0. And we have this thing over here, right? Now we can make some further simplifications. What we can do is, since we know that our like main differential equation was just y double prime plus p1 of x y prime plus p2 of x is equals to 0. Sorry, p2 of x y is equals to 0. We can use this to get we can get negative p1 of x y prime negative p2 of x, right? Over here, negative p1 of x, sorry, this is y1, and this there's a y1 over here, I'm sorry, and then yeah, y2 prime minus p2 of x y2, right? So this becomes Wronskian prime is, now again, you know that like even if you add a constant multiple of a row with another row, the determinant remains unchanged, right? So what you can basically do is you can add p2x times row 1 with second row. So what you can do is basically, if row 2 is row 2 plus p2x times row 1, the determinant is unchanged, so we still have that equals Wronskian prime. This becomes y1, y2, negative p1 of x, y1 prime, negative p1 of x, y2 prime, right? So you see, now if I just take, we can, I think you know that if a row or a column has the same constant multiple, I mean, if it's multiplied by the same thing, you can take that common, right? So yeah, if you use that property, now you might notice that this determinant just becomes the Wronskian again. And that's an important thing for us. Now we see that this Wronskian prime is just negative of p1 of x times Wronskian again. Now we know that this is just a simple, like, well-known differential equation, right? We have solved this many times. Yeah, so basic derivative is proportional to itself times some multiple, and we know that the solution for this is the thing that was there, some constant times e to the power integral of this function. We can write the integral as, again, basically if because it starts with t naught, so from t naught to t, and then yeah, negative sign from this negative p1 of x, so that's where the sign comes, and then p1 of x dx. So yeah, that's how this formula is proved. Now let's just use this formula to find Wronskian for this function over here. After that, we will also try to find Wronskian of this nth order differential equation. So first of all, let's do it for this problem. t to the power 4 negative 2t cube t to the power 8, right? Yeah. So given problem is t to the power 4 y double prime negative 2t cube y prime minus t to the power 8 y is equals to 0. So first of all, we have to take it to this form over here, this form, so that there's no function in front of y double prime. If we do that, we get y double prime minus 2 by ty prime minus t to the power 4 y is equals to 0. Now we know that Wronskian will just be some constant. It's some any number t naught, you can pick anything, and then e to the power negative of integral from t naught to t, and then negative of our p of x, right? In this case, our p of x is negative 2 over t, and then basically, but I should, t is already there in the limits of integral, so let me write this as function of x, negative 2 over x dx, right? So Wronskian will be some constant times e to the power. Now this will just be integral from t naught to t of 2 over x, right? And e to the power, this is just 2 times ln of modulus of x from t naught to t. But since there's t in front, I can basically remove the modulus and make it just ln of square, x square, right, from t naught to t, and that also becomes e to the power ln of, this becomes basically there's a difference, so t square by t naught square, right? And yeah, e to the power a and ln cancel out, and that gives us basically some constant times t square, right? And yeah, that's the Wronskian. So we could find out the Wronskian even without actually solving it, and that's how this formula is helpful. Now, since we know that, since we saw that it actually works, I mean, I didn't show you it works or not. I mean, because we didn't find out the Wronskian explicitly, but still we saw that we could find it out, right? Okay, now let us try to do it for nth order, and then we are done. So let's see how we can find out Wronskian, like from an nth order differential equation. So basically, there's this y, which is nth order, right? Yeah, and then there's this p of n minus 1 x times y n minus, this is n minus 1th derivative, okay? And maybe p n minus 2, n minus 2, and then it goes on. Maybe there's p2 of x, y double prime, plus p1 of x, y single prime, plus p naught of x, y is equals to 0. We need to find its Wronskian, right? Okay, again, just like the previously, we know that Wronskian is again for this defined as, if it will have n solutions, right? And like fundamentals, I mean, yeah, and fundamental solutions. So y3, yeah, there will be n solutions, and I don't think we have issues over here. And yeah, now second row will just be their derivative, right? And third row will be their double derivative, and it goes on. And in last row, we will basically have its nth derivative, right? Yeah. Now we know how to find derivative using the formula of Leibniz, right? So if we do that, we basically differentiate row by row. So first of all, there's y1 prime, y2 prime, y3 prime. I think you see the benefit of doing it this way, right? Because you see that first and second row are identical now, right? And we know that if two rows are identical up to a constant, their derivative is just 0, no? And that's how it's helpful. And yeah, so I'm writing it just for formality, but we already know that this is gonna go to 0, right? Again, observe, now again, even the second matrix is going to go to 0, because the first row is just as usual. And now if you take a derivative of second row, this is gonna have double prime. And we know that even the third row has double prime, right? So again, two rows are identical out to a constant. And again, because of that, the determinant is gonna go to 0, right? And yeah, in this way, actually, except the last determinant, all of them will go to 0, and that's a really uh, beautiful thing for us, right? Okay, now since we know that even for the, like, if we take this, like, even if you turn up the, like, second last row to get derivative, that will just become identical to last row, and that will be 0, right? So we will just skip all of them that are going to 0, and we will directly write the last one, and last one will not go to 0 because that will not be identical to any of this. And I forgot something. Actually, I forgot something because, oh wait, in Wronskian, for this case, we only took determinant up to first derivative, right? Not up to second. So over here, it will have derivative up to n minus 1, not up to n. I'm sorry for that. I'm sorry for that. I'm sorry for that. It will have derivative only up to n minus 1. N minus 1. Okay, not up to nth, because in the second like order differential equation, it had only up to the first derivative, right? So similarly over here, up to n minus 1 derivative. Mess that up. I always miss something. I'm sorry. Okay, now okay, now I have already told you that up to the derivative of second last row, that's gonna go to 0. So now, like, only the case where we take derivative of last row, that will not vanish, right? So that will not vanish, and yeah, that's what I'm gonna write. Okay, and yeah, now finally, because we took derivative, this is gonna become n, right? Yeah. Now I have already told you that let's write it this way so as to symbolize the derivative. Now I already know that uh, all of these are gonna go to 0, right? Because they have two identical rows, 0, right? And only the last one remains. Now let's see. Now the last one will be, okay, y1, y2, y3 up to y1, y1 prime, y2 prime, y3 prime up to y1 prime, double prime up to yn double prime, and so on, right? And okay, now again we can write last row using our, like, differential equation. We know that we can write it as this whole thing going to the other side, right? So this becomes negative p n minus 1 x y n minus 1, negative p n minus 2 x y n minus 2, negative p n minus 3 x y n minus 3, and blah 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 up to negative. And also there should be y1, 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 right? Also, let me give some space over here because I don't think the space will be enough. Let me give a little bit of space over here. Let me give a little bit of space over here. Yeah, I think that will be enough now. Also, what I can do is I can take this a little bit to the, I can take this a little bit other side, and then I can give them some space now. Yeah, okay. Now, yeah, and the last thing is negative p2 of x y1 double prime, negative p1 of x y1 prime, negative p0 of x y1, right? And similarly, and I think I will need a little bit of space over here at last, so I can just shift it a little bit over here. Okay, and then, okay, over here also we will have y to the power n, right? I mean nth prime, right? So this will be negative p n minus 1 x y2 n minus 1th prime. This is a derivative, okay, not just some power, minus p n minus 2 x y2 to the n minus 2th prime, and so on, of negative p1 of x y2 first prime, negative p0 of x y2, right? And that's the same thing over here. I mean, yeah, you get the idea, right? What I can do is I can just copy this, I guess. I can just copy this and paste it here. paste, but except that I have to change 2 to 3, 3, 3, 3. I can do that. I can do that. Right. Copy this. Paste it over here. Also make it little so small. Right. And again replace y3 by y1 yn now. y3 by yn. Right. yn 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 yn. Okay. And the determinant. Now notice that I can actually simplify the determinant if I multiply last row. If I change the last row, since I can add a multiple of one row with another and determinant remains unchanged, so what I can do is last row I want to add like p0 x times the first row plus p1 x times the second row, right? I actually meant to write the second row, because if I add like this times first row here, p0 x times y1 is added, that cancels this term over here, right? So I'm basically trying to cancel these terms, right, as much as I can. We know that, and also know that like just above the last row here is a row with power n minus 2, right? Definitely know that thing. We will need that. Okay, so maybe you can notice that just above the last row there's a term over here with n minus 2th like derivative, but like n minus 1 derivative was there at the last, but since now we have the derivative that doesn't exist, so we can actually remove all the terms up to n minus 2 but not the one with n minus 1. Okay, please do know that. Okay, yeah, so what I'm doing is this thing, and then p1 of x times r2 of x, and then p2 of x times r3 of x, similarly up to this pn minus 2 of x times r of n minus 1x, right? So if we do this, we will have the following expression now. What we will have is Wronskian prime is equals to this will be y1, y2, y3 up to y1, y1 prime, y2 prime, y3 prime, yn prime, and up to the last over here I will have basically n minus 2th prime, n minus 2th prime up to yn to the power n minus 2, and last thing will now be yeah, this negative of negative pn minus 1 x times y1 to the power n minus 1, right? And negative pn minus 1 x times y2 to the power n minus 1, so on over here, negative pn minus 1 x times y1 to the power n minus 1. So now I can basically take this negative pn minus 1 x common, and the remaining thing is just Wronskian, right? So times Wronskian, and that's how we get Wronskian to be equals to Wronskian at some t to be equals to Wronskian at some t naught times e to the power negative. Basically not negative, but this sign over here will, okay, from t naught to t, and then negative pn minus 1 x dx, and that gives us Wronskian to be equal to Wronskian at t naught times e to the power negative for integral from t naught to t pn minus 1 x dx. And that's how we get this expression for person nth order differential equation. At this point, I do feel that instead of doing for nth order, I should have just done for third or fourth order, and that would have made it pretty clear. I realized that doing for nth order makes it a bit vague and unclear. Actually, doing for like some third order would have made more sense. But yeah, I think you got the idea. You can just generalize this second order argument to anything, right? And that's it basically. So I hope you enjoyed the video. So we have done all of this, and I hope it was helpful. Thanks for watching, and I look forward to seeing you in the upcoming videos too.